Okay, welcome students. In the last lecture, we discussed regarding Coulombs law, electric field, electric forces and related information. And in the current lecture, what we'll do is, we'll try to solve certain problems based on these previously discussed topics. Now, we have written here a problem which was recently asked in JE. The problem states that we have two equal negative charges, each having magnitude minus q. They are fixed at points 0a and 0 minus a on y-axis. A positive charge plus q is released from rest at point 2a 0 on x-axis. Now, what we are asked is the charge will, and these are the options given to us. The charge will execute simple harmonic motion about origin, or the charge will move to the origin and remain at rest, or the charge will move to infinity, or the charge will execute oscillatory motion but not simple harmonic motion. Now, this is the thing which we are supposed to look at. But before going into the problem, there are some concepts involved related to simple harmonic motion or the oscillatory motion. We should be familiar with the stuff that for a motion to be called a simple harmonic motion, it should obey Hooke's law. And the Hooke's law is restoring force should be directly proportional to displacement, linear dependence on displacement and directed opposite to it. Now, our first concern here should be that we will be drawing the free body diagram for this very stuff. Okay. Now, what we are given is we have two charges minus q each which are placed on y-axis. So let's suppose this is our y-axis and this is our x-axis. We have two charges. We have one charge here having magnitude minus q and another charge here which is also having a magnitude of minus q. Let's call this as origin O. So the distance from this point up to this is A, and this distance is also A. Because drawing the free body diagram is the most important step as far as the solving a particular problem is concerned. So the first part of the problem as far as the free body diagram is done. We have two equal charges minus q, they have been placed on y-axis at a distance a and minus a respectively. Then what we are asked is, we have another positive charge of magnitude capital Q. It is released from rest at a point 2a0. Let's suppose the distance from here up to this point, say this point, this is 2a. Let's call this point suppose P. You are releasing a charge capital Q, which is positive in nature. Now this negative charge will attract that positive charge, this negative charge will also attract that positive charge. Means both these charges will attract that positive charge, and at a particular instant, suppose this charge is at this point, let's call it Q. Because this charge at P, this will be coming closer because of the attractive electrostatic force. So let us suppose this charge is at, let's give this some name, suppose S. We have a charge which is capital Q. This is point S and a charge capital Q is there. Let's suppose this distance from here up to there, this distance is x. This is our free body diagram. Now this, let's suppose this negative minus q, this will attract this positive charge and let's call this angle as theta. Similarly, this minus q will also attract this charge, and with the same distance this will be theta. So minus q will attract this plus q, and this minus q will also attract this plus q. Now what we are supposed to calculate is, we are supposed to look into the issue what will be the nature of the motion of this charge q. Now, whether it will be simple harmonic motion, whether it will be oscillatory motion, not simple harmonic, whether the charge will come to the origin and remain at rest, or the charge will come and move to infinite distance. So, for that particular purpose, we should know the nature of the force involved. We should know the dependence of force on distance. Because we mentioned earlier that suppose for the motion to be simple harmonic, we should have linear dependence of non-distance. So we should have the nature of the force in this particular case. Okay, now the force of minus q on this capital Q, suppose this will be in this direction, this will be attractive. Similarly, force of this minus q on this charge will also be on this direction, this will be here. And the force, these distances will be equal. Suppose let's call this is O, this is charge q here, point S. Let's call this M, this point as M, and this point as N. Now, in this particular case, according to Coulombs law, because Coulombs law gives us the electrostatic force between two charges at rest, we state that the force between two charges at rest is directly proportional to the product of two charges and inversely proportional to the square of the distance between them. And by incorporating the electrostatic force constant, you have Coulombs law in this form: F is equal to K, or 1 by 4 pi epsilon naught. You have between these two charges, between minus q and capital Q, this will be equal. In general, it is Q1, Q2 divided by R square. This is the Coulombs law. So in our case, one charge is minus q, the another charge is plus capital Q, and the distance between the two charges, let's call this distance as R. This distance is R. This distance is R. In both cases, let's call force due to this charge as F1, force due to this charge as F2. These two forces, now if we see the nature of these two forces, suppose let's calculate F1. F1 will be 1 by 4 pi epsilon naught Q1, that's minus Q, Q2, second charge is capital Q, divided by distance between the two charges, that is R, means R square. Similarly, force F2 here, this will be equal to 1 by 4 pi epsilon naught minus Q is the one charge plus capital Q is the another charge divided by same distance R square. This is force F1 due to charge minus Q. This force F2 is due to charge this minus Q placed on the negative y-axis. Now, if we have a look at these two forces, what we see here is that these two forces are equal in magnitude, but they are not in same direction. They are equal in magnitude. We can see from here every term is same, so they are equal in magnitude. But F1 is directed in this direction and F2 is directed in this direction. So we can mention the direction. This is along SM. This is along SM, and this force is along SM. This is along SM. So the total we have to take the sum of both of these forces. But what we do is we can resolve these two forces into components, F1 and F2. See, had these F1 and F2 been in same direction, we'll simply take sum of the two. Had they been in opposite direction, we'll take the difference of the two. That is how we go for the vector addition or subtraction. But F1 and F2 are inclined at some angle, this much of angle. So what we'll do is, we'll resolve this F1 into rectangular components. Similarly, we'll resolve this F2 into rectangular components. If we resolve this F1 into rectangular components, this will be F1 sine theta, and here along this axis we will have F1 cos theta. Similarly, once we resolve F2 into rectangular components, this will be F2 sine theta, and along this axis we will have F2 cos of theta. Now from here what we can say is F1 is equal in magnitude to that of F2. Or we can show the vector notation here as well. F1 and F2 both are same in magnitude, but obviously direction is different. But see here, now if F1 and F2 are same in magnitude, so what we can say is F1 sine theta and F2 sine theta, since they are equal in magnitude but opposite in direction, they would cancel. So the sine components would cancel, which means we can write here F1 sine theta and F2 F2 sine theta would cancel. So F1 sine theta and F2 sine theta will cancel. And F1 cos theta and F2 cos theta are in same direction. Since F1 cos theta and F2 cos theta are in same direction, hence they would add. Hence they would add up. So the net force will be F1 cos theta plus F2 cos theta. So we have the net force. This will be equal to, since F1 and F2 is equal, it will be F1 cos theta plus F2 cos theta. Since F1 and F2 are equal, we can write it is twice F cos theta. Twice F cos of theta. Okay, let's call, we can give this some arbitrary number to this equation. Let's give this equation number 1. Now we will try to say is, according to Coulombs law, we know force between two charges. So now, F we know, as far as the magnitude of F is concerned, this is, according to Coulombs law, 1 by 4 pi epsilon naught Q1. One charge is minus Q. So if you take away the magnitude, it will be Q. Second charge is capital Q divided by R square. This is F. Also, cos theta. If we take this right triangle, MOS. So in right triangle, MOS will have cos of theta based upon hypotenuse. Base is this OS and hypotenuse is MS. So it is OS by MS. OS by MS. Now we know OS, this is equal to X, and MS, this is equal to R. So this is, let's call this equation as 2, let's call this one as 3. Now we can write this R into, see, this is A and this is X. So also from this same triangle, right triangle MOS, if we use Pythagoras theorem, we'll have R square, hypotenuse square is equal to base square plus perpendicular square. So R square is equal to X square, which is base, and perpendicular square is A square. It means R square is equal to A square plus X square, or you can write R is equal to A square, the square we can take here, it will be root, plus X square power 1/2. Let's call this equation as 4. So in equation 1 now, we'll use value of F from equation 2. Also we'll use a value of cos theta from equation 3. So using 2 and 3 in 1, using equation 2 and equation 3 in equation 1. Just see here, what we are doing is, we are putting the value of F from equation 2 in equation 1, then we are putting the value of cos theta, which is X upon R, from equation 3 in equation 1. So what we'll get is, here, net force. What is this net force? This is the net force acting on this charge capital Q due to these two charges minus Q each. So F net will be equal to, this is twice into F. F we have here 1 by 4 pi epsilon naught. Obviously you have taken only the magnitude of these charges. This is small q into capital Q and then r divided by r square. R square also we can put it from here. Okay, for the time let it be r square into cos of theta. Cos of theta. Cos of theta is x by r. So it is x divided by r. Okay. Now let's call this as equation say 5. Now what we can do is we can use value of r from equation 4 in equation 5. So using equation 4 in 5. Using equation 4 in equation 5. What we'll get is net force. Even if we take the negative sign also here, then we can also have this negative sign there, negative sign there. Magnitude it will be 2 into 1 upon 4 pi epsilon naught. This is small q into capital Q divided by, this is r square into r means r cube. But r is equal to this much, so this will be a square plus x square raised to the power of 3 by 2 into this x. So this is the final expression we are getting for the net force acting on this charge plus q, which is at a distance 2a from here, by these two charges minus q each, which are placed on the y-axis. And if we don't use only the magnitude here, then we will also get a negative sign there, but magnitude of the force is this much. Now we have calculated the magnitude of the net force acting on this charge, but we are not asking for any expression regarding the force. What we are given the options like this, that what will be the nature of the motion of this charged particle plus q. Now whether the motion will be simple harmonic motion, whether the charge will come to the origin and remain at rest, or whether the charge will, because this will be attracted, it will come to the origin and move to the infinite distance, or whether the motion will come towards the origin, the motion will be oscillatory but not simple harmonic. Okay. Now we know for simple harmonic motion, we know F raised to force is proportional to minus distance. There is a linear dependence. In simple harmonic motion, there is a linear dependence of force on x. The power of x has to be 1. That is the relation between force and the displacement. But if we would analyze this equation, we see here the dependence between force and x is not linear, because x is involved in the denominator as well. So what we can conclude here, that the relation between force and x is not linear. So I can write here the relation between F and x is not linear. This is not linear. Hence, motion is not simple harmonic. Since the relation is not linear, motion is not simple harmonic. So motion will be oscillatory but not simple harmonic. Hence the motion is oscillatory but not simple harmonic motion. So the motion will be oscillatory. Oscillatory because these negative charges will attract this positive charge towards the origin, but it will not be simple harmonic because the relation between force and displacement is not linear. So we have here the fourth option, that the particle will execute, or the charge q will execute oscillatory motion but not simple harmonic. Okay, now our next problem is based on the surface charge density, and it will also incorporate the concept of charge by induction. The problem given to us is, we have three concentric metallic spherical shells and they are given charges Q1, Q2 and Q3. And these charged shells have radius, since they are concentric, their radii are R, 2R and 3R respectively. Then it's found that the surface charge densities on these spheres are equal, and in that case we have to find out the ratio of Q1 is to Q2 is to Q3. This ratio we have to find out. Now, before going for the diagram and calculations for analyzing this particular problem, what we need to do is, what are the concepts which we need to incorporate while analyzing this particular problem? That's one, the surface charge density. Surface charge density, we have a linear charge density, we have surface charge density and volume charge density. Surface charge density is charge divided by area. So that thing will incorporate while solving this particular numerical. And then apart from that, we should also have the concept of charge by induction. We know charge gets transferred by conduction, where there is a physical contact between two bodies, but charge also gets transferred from one body to another by virtue of induction. So that charge by induction will also be incorporated in analyzing this particular problem. So let's make the diagram for this particular problem and we'll try to see there. Suppose this is the first spherical shell having radius r. These are three concentric spherical shells we have to show. Let's suppose these are the three concentric spherical shells. The radii of first shell is r. The radii of second shell, this is 2r, and radii of third shell, this is 3r. So this is the radii of three concentric shells, r, 2r and 3r respectively. And we are giving charge q1 to first shell, charge q2 to the second shell, charge q3 to the third shell. But what will happen once we give charge q1 to the first shell, a charge minus q1 will be induced on the inner side of second shell, and a charge plus q1 will be induced on the outer side of shell 2. So if we see what is the net charge on the second shell, outer side of second shell, that is q1 plus q2. Okay, now as far as third shell is concerned, third spherical shell is concerned, this already has a charge of q3, but this on the outer side of second shell, you have now a charge of q1 plus q2, because q2 was the original, q1 is due to charge by induction. So this charge minus q1, this charge q1 plus q2 will induce a charge minus q1 plus q2, means equal in magnitude but opposite polarity. This charge will be induced to inner side of third shell, and similar magnitude of charge will be induced in outer side of the third shell. So if we see total charge on outer side of third shell, that is now q1, this much, q1 plus q2, and original charge is also q3. So this total charge on the third spherical shell is q1 plus q2 plus q3. The total charge on the second shell is q1 plus q2, and the total charge on the outer side of shell 1 is q1. This is the preliminary concept which you have to understand before proceeding further. Then, in the question we are given that the surface charge densities on these spheres are equal. Now, what about the surface charge density sigma 1 of the first shell? Surface charge density is charge divided by area. So it is charge q1 divided by area, surface area, that is 4 pi r square. Let's call this 1. Surface charge density of first shell. Similarly, surface charge density of second shell. What is the charge on second shell? q1 plus q2. And what about the area? 4 pi. What is the radius of second shell? That is 2r. So it will be 4 pi into 2r whole square, which means it is q1 plus q2 divided by, you can have it 4 pi into 2 square is 4 into 4r square. Let's keep it this way for the time being. Let's call this as equation 2. Now, what about the surface charge density of third shell? we'll have the surface charge density of third shell. It is charged on the third shell. That is Q1 plus Q2 plus Q3. That's Q1 plus Q2 plus Q3 divided by surface area of third shell. That is 4 pi. And what about the radius? 4 pi r square. What about radius of third shell? That is 3r. So it will be 4 pi into 3r square. So it will be Q1 plus Q2 plus Q3 divided by 4 pi into 3 3s is 9. It is into 9r square. Let's call this equation 3. So these are the surface charge densities of 3 spherical shells having radii r, 2r and 3r respectively. But what is the condition given in the question? It is found that the surface charge densities on these spheres are equal. So what we are given is, we are given the condition that sigma 1 is equal to sigma 2 is equal to sigma 3. This is given because surface charge densities on the shells are equal. This is given. So let's call this equation as 4. So if we use 1, 2 and 3 in 4, so using equation 1, 2 and 3 in equation 4, just try to equate them. So sigma 1, we have Q1 by 4 pi r square. This should be equal to surface charge density of second. That's this much. Q1 plus Q2 divided by 4 pi into 4r square. This should be equal to surface charge density of third shell. That is Q1 plus Q2 plus Q3 divided by 4 pi into 9r square. Okay. Now if we have some similar terms on the equation, we can have some cancellations. 4 pi is throughout. So 4 pi we can cancel throughout. And r square also here, r square here and r square here, this cancels out. Now what we are left with, we can see from here. Q1 is equal to Q1 plus Q2, Q1 plus Q2 divided by 4, which is equal to Q1 plus Q2 plus Q3, Q1 plus Q2 plus Q3 divided by 9. So we're almost done. We just have to now use some simple algebra to find the relative ratio of Q1, Q2 and Q3. Now what we can do is, if we equate these two parts, multiplying 4 with this Q1, we'll have 4 times Q1 is equal to Q1 plus Q2, Q1 plus Q2. Now bring this Q1 here, you will have 4Q1 minus Q1 is equal to Q2. Or you will have 3 times Q1 is equal to Q2. This is one relation. Let's go. We have some numbers here. This is equation 4. Let's call this whole as equation 5. And we can call this as equation 6. Okay. Now also what we do is, we can use this value of Q2 here in this equation. So you have here, if you equate these two here, you have Q1 is equal to, it is Q1 here plus, in place of Q2, I will be writing 3 times Q1. So it is 3 times Q1 plus, we have Q3 already there, so it is Q3 divided by 9. So simplifying it, it is 9 into Q1, it is 9 times Q1 is equal to Q1 plus 3Q1, that is 4Q1 plus Q3. Or we have 9Q1 minus 4Q1, this is equal to Q3. Which means Q3 is equal to 5 times Q1. So the final ratio between Q1 is to Q2 is to Q3 is equal to, if we take Q1 as 1, now Q2, it is 3 times Q1, so it will be minus to 3. And this Q3, this is 5 times Q1, so it will be 1 is to 3 is to 5. This will be the final ratio between the charges on these 3 concentric spherical shells. Okay, the next problem given to us goes like this. We have given that we have 2 identical charged spheres suspended from a common point by 2 massless strings of length L are initially at a distance d apart, where d is much less than L because of their mutual repulsion. The charges begin to leak from both these spheres at a constant rate, as a result of which the spheres approach each other with a velocity v. Then what we are supposed to look at is the relation between v varies as a function of distance x between spheres as. Now, before going into the physical aspect of this problem and try to look out the relation between v and x, it would be better to put these things in the graphically and try to correlate it with what the given circumstances. So we have here, what we are given is, we have here a situation like this. 2 spheres are suspended from a common point. Let's suppose this is one sphere and this is another sphere. They are suspended from a common point. And because these spheres, let us suppose charge on this sphere is Q, identical charged spheres, charge on this sphere is also Q. Now, because of the mutual repulsion between these 2 spheres, they are this much apart. Had these 2 charges been had the 2 spheres been neutral, these spheres would have been at their mean position. But because of repulsion, they are held at this distance. Okay. Now let's call this point O. Let's call this point M, N, and this is as R. Let's call this angle as theta. Okay, these are 2 charged spheres which are held at a distance. Earlier they are held at a distance d apart, and this length of the strings is L. Okay, now what happens is initially they are at rest at a distance d. But after that, because of a repulsion, because there will be electrostatic repulsion between these 2 charged spheres. Now, after that, what happens is the charges begin to leak. So this was a charge Q, now this charge begins to leak. Some of the charge leaks out. Similarly, from this, some of the charge leaks out. But with a constant rate, means charges leak at a constant rate. And at a particular point, suppose distance between these 2 charges is x. Distance between these 2 charges is x, and these two charges are approaching each other, because once the charge leaks, electrostatic force of repulsion would decrease and these charges will approach each other. These 2 charges approach each other with a velocity v, and we have to find the relation between v and x. Okay. Now, for that purpose, what we need to do is, the first thing we need to do here is we need to find out, suppose if we take one particular charge, we need to look what are the forces acting on that particular charge. Now let's suppose if m is mass of each charge, if m is mass of each charge, so the various forces acting on, there will be one force, that is weight of the body acting vertically downwards, mg, weight of the body. G is acceleration due to gravity. This is one force. Second force, there will be electrostatic force of repulsion in this direction. And how much will be that? F will be equal to K, which is 1 by 4 pi epsilon naught, Q1, Q2, it will be Q into Q, that is Q square, divided by distance between the two charges, that is x square. So this will be the electrostatic force of repulsion acting here. K, which is electrostatic force constant, equal to 1 by 4 pi epsilon naught divided by distance square, that is x square. And also there will be tension in the string in this direction, that's T. Tension T. So the forces acting on this particular charge are Q1, the mg, which is weight of the body acting vertically downwards. Then there is electrostatic force of repulsion, K, Q square by x square, and also there will be tension in the string, that's T. Now if we can resolve T, the tension, resolving tension into rectangular components, if we resolve it into rectangular components, we will have rectangular components will be here this way, and it will be this way. If this angle is theta, this angle will also be equal to theta, and then this will be T cos of theta, and this one will be T sine of theta. Fine. Now since initially this charged particle is held at rest, which means there is equilibrium of concurrent forces, or the net force acting on this charged particle is zero, because in only that case the charged particle here is at rest. Which means total force is zero, which means T sine theta has to be balanced by this electrostatic force of repulsion, and the weight of the body mg is balanced by the cosine component of the tension. So since initially, let's write it this way, since initially sphere is at rest, which means T sine theta will be equal to K Q square by x square, K Q square by x square, and T cos of theta will be equal to T cos of theta will be balanced by weight of the body, that's mg. Okay, this is suppose equation 1, this is equation 2. If we divide 1 by 2, if we divide equation 1 by equation 2, T and T will cancel, sin theta by cos theta is tan theta. This is equal to kq square by x square into 1 by mg. Okay, this will be tan of theta. But since we are given a condition here that d is much less than L, means this distance d by which they are separated, this is much less than L, means the length of the pendulum is much greater than the distance separation between them, which essentially means that theta would be very small. And in case, so let's write it this way, since d is much less than L, which is given, which means theta is very small. And in case theta is very small, we know sin theta is equal to tan theta. In case theta is very small, sin theta is equal to tan theta. And what will be sin theta? In this, from this triangle, it will be perpendicular by hypotenuse. Perpendicular, or this will be the perpendicular by hypotenuse. Perpendicular is mn divided by hypotenuse. Hypotenuse is OM. Which means this is equal to mn. See, total here, this is x. So mn, this will be equal to x by 2. And this much will also be equal to x by 2. And this is equal to L. So this will be equal to x by 2 divided by L. Or this is equal to x by 2L. Let's call this equation, let's say this one was 3. Let's call this 4. So if we use equation 4 in equation 1, using equation 4 in equation 1, so using equation 4 in equation 3, using equation 4 and equation 3, what we get is, in place of tan theta, I'll be writing x by 2l. This is equal to kq square by x square into mg. Or simplifying it, taking q square on one side and x, all the other terms on the other side will have q square is equal to, this will be x cube, x square into x is x cube multiplied by mg divided by, this is x cube mg divided by k into 2l or 2kl. So this is the expression for, this is the relation between charge and other related stuff. In this case, mass of the particle, acceleration due to gravity, the electrostatic force constant and length are constants. So essentially we get q square is proportional to x cube. Or we can say that q is proportional to x raised to the power of 3 by 2. Q is proportional to x raised to the power of 3 by 2. Now, if we differentiate this, if we differentiate it with respect to time, if we differentiate it with respect to time, we'll get dq upon dt. If we differentiate this with respect to time, we'll get it dq upon dt. This is equal to or proportional to, differentiating x with power 3 by 2, it will be 3 by 2 times x raised power of 3 by 2 minus 1, that's 1 by 2 into dx by dt. Now dx by dt is velocity, and we are given that dq by dt is constant. dq by dt, this is constant. This is given condition. That charge is leaking at a constant rate, means dq by dt is constant. So what we can write here is 3 by 2 into x raised power 1 by 2 means root x into dx by dt, this is velocity. dx by dt is velocity. This is constant. Or v is equal to 2 by 3 into constant divided by root x. Okay. From this equation, what we can conclude is the relation between v and x, which is v is inversely proportional to root x. This was the thing which we were supposed to calculate, that v is inversely proportional to x.